let's do a simple robot. What's a simple robot? How about this? Okay, that's about the simplest robot I can think of. Okay, all right, let's write down the forward kinematics for this. This is a silly one-joint arm. Okay, so let's call this theta 1, only one joint. Okay, and I'm going to just assign arbitrary frames, arbitrary fixed frames. So here's fixed frame. Okay, here's my fixed frame. X-axis, y-axis, z-axis. Okay, and I don't know anything about DH parameters. Okay, so I don't know that you have to be careful on how to attach the hand frame. Okay, so I'm going to say this is my hand frame. Okay, X, Y, Z. Okay, here's my hand frame. Okay, let's write down the forward kinematics using what we just learned. Okay, so how can we do that? Well, if you think about what this joint is, what is this joint? It's just a screw motion, okay? We're applying a screw motion to this frame. Okay, so what's the screw axis? Screw axis is the joint axis. Okay, and what's the pitch? Pitch is 0. It's just a pure rotation, right? It's not doing this. It's just a pure rotation. Okay, so that's a very simple screw, very easy, right? All right, so it's not hard to see that we can just write T0H, okay, is equal to what? Some screw here, omega hat V00 times theta 1 times what? Times what? Times this transformation, right? Times this transformation. Okay, so we need to know a few things. We need to know, for example, what this height is. Let's say that's L1. We'll say this is L2, the link length. Okay, so it's this times what? Some matrix here. So that's just frame H as seen from frame 0, okay, when theta 1 equals 0. Okay, so this configuration shown in the figure. Okay, so if we look at what that is, let's see, the orientation is the same. Okay, so that's I. Then we have 0 here, 1 here. And let's see, in the x direction, 0. In the y direction, we need to move L2. In the x direction, z direction, we need to move L1. Okay? So T0H is going to be of this form. Okay? So think about it. When theta 1 equals 0, when theta 1 equals 0, what happens? When theta 1 equals 0, this is the exponential of 0, which is I, the identity. Okay? So then we're left with this. Okay? So that's a good way to check. Okay? When theta 1 equals 0, is the hand frame at this frame? Yes. Okay? So this is just the hand frame in the 0 configuration, or the home position of the robot. Okay? So that's how we start. Now, we have to find this. We have to find these two things. Okay? So let's see. Omega hat is what? Omega hat, I said, is the unit vector in the direction of the screw axis. Screw axis is in what direction? It's in the z direction, unit vector. So it's just 0, 0, 1. Okay, that was easy. Now it's V. Well, in order to find V, well, we said V is minus omega cross Q plus H omega, where Q is what? Q is any point on the screw axis, or in this case, the joint axis. So Q can be any point on this axis. Okay? So it can be this point, this point, this point, this point. Doesn't matter. You pick. Pick your favorite. So if it were up to me, I would pick this. Okay? The 0 point. That's easy. Okay? So Q equals 0, 0, 0. And H, what's H? H is the pitch of the joint. Okay? What's the pitch here? 0. Okay, easy. All right, so V is pretty easy, 0. Okay, you're done. Okay? All right, so that was an easy example. That's too easy. Okay, let's make it a little bit more challenging. Okay, but not too challenging. Okay, let's do this one. So here's my hand frame. Here's my 0 frame. Okay, let's do that. Now, I'm going to guess that this is going to be of the form e to the s1 theta 1 e to the s2 theta 2 times some m. Okay. Now, why can I make this guess? Why is this reasonable? Well, if you think about it, so here's theta 2, here's theta 1. Okay. Oh, got it backwards here. Theta 2, theta 1. Okay. So if you think about it, e to the s2 theta 2 times m. This is applying a screw motion to m. Okay, so what is m? So think about it. When theta 1 equals 0 and theta 2 equals 0, this is I, this is I. So T0H equals m. So m is just the hand frame when all the joints are 0. Okay, so in this case m is what? Orientation is the same as the fixed frame. That's I, 0. Okay. And, we just need to write down the position of this frame. So that will be 0. Oops, I left out something here. There's a 0 at the top. Okay. And then this would be L2 plus L3 and L1. Okay, so there's my m. There's my m. Okay. Now S2. So S2, this S2 is omega 2, V2, 0, 0. Okay. So that's my screw. That's a screw for joint 2. Okay, so joint 2 is applying a screw motion to this frame. Where's the screw axis? That's the joint 2 axis. Okay, what kind of screw motion is it? It's a 0 pitch screw motion. So all these screw motions are 0 pitch. Right? Unless if you have a real screw joint. But we don't really use real screw joints. Okay, they're all pure revolute joints, right? Okay, so omega 2 is the screw axis for joint 2. And what direction is that? That's in the x direction, right? So it's this direction, which is the x-axis. So this is just 1, 0, 0. Okay? And then we need to find V2. But before finding V2, let's find Q2. So Q2 is any point on screw axis 2, joint axis 2, any point. So it could be this point, this point, this point. This point seems like a good choice. Okay, why not? Okay, so Q2 is 0, 0, and I guess we call that L1, right? Okay, so V2 is minus omega 2 cross Q2. Okay, so just take the cross product, right? X cross C minus Y plus Y. So this is 0, L1, 0. And of course, the pitch is 0, so there's no second term here. Okay? Done. Done. Okay. Okay, question is what is L1, L2, L3? Okay, so this is L1 here. That's L1. Oh, actually, you know what? I got ahead of myself. There's no L3 here. Yeah, sorry. Yeah, it's just L2. Okay, yeah. Okay. Okay. Now comes L3. Okay. All right, so now another example. So we're going to reuse this picture. Actually, no, we can't reuse this picture. Okay, so third example. Okay, let's do that. Add another joint. Okay. Okay, let's put the fixed frame, or hand frame here. Fixed frame here. Okay. Okay. Theta 1, theta 2, theta 3. Theta 1, theta 2, theta 3. Okay, and now there is L1, L2, L3. Okay, so there's your L3 now. Okay, let's do it again. Three joints. Okay, so it's going to be of this form. Okay, so what's M? Well, orientation part is I. And this is 0, L2 plus L3, L1, 0, 1. Okay. S1. S1. Do we need to do this again? Does anything change? S1. S1 is the screw for joint axis 1. Same as before, right? Same as before. S2. S2. It's this, right? Same as before. Okay, S3. Let's find omega 3. The screw for joint axis 3. Joint axis 3 is pointing in which direction? Pointing in the x direction. 0, 0, 1. Now let's find the point on joint axis 3, any point. So we have a lot of choices here. Okay. A convenient one seems to be this point here. Okay, so that is 0, L2, L1, I believe. Okay, and then once you have omega 3 and Q3, simple matter to find V3. Oh, sorry. 1, 0, 0. Okay, and then V3 is minus omega 3 cross Q3. So, you can, okay, so you can just do this, right? Okay, calculation. All right, so you get the idea here. Okay. Pretty easy, right? Pretty easy. No link frames. No link frames. That's great. Okay, that's progress. Okay, no link frames. Finding these omegas and v's, pretty easy, right? Just find the joint axis. Okay. Find the joint. Put the robot in the home position, in the 0 position. Okay, make sure it's in the 0 position. Define a fixed frame. Okay, and then just write the joint axes as unit vectors. Those are your omegas. Okay, and then find points on the screw axes, on the joint axes, the q's, and then just do minus omega cross q. Okay. All right, so pretty nice. There's one small detail we haven't covered. Prismatic joints. What do we do about prismatic joints? Okay. Well, when you have prismatic joints, okay, what does a prismatic joint do? It moves it translates the frame, okay, while keeping the same orientation. Okay. So if we have some frame, okay, something like this, okay, it's always the same orientation. Okay, so in the case of prismatic joints, omega hat is always 0. Okay. And V is a unit vector. Well, we'll take it to be a unit vector. Okay, in the direction of translation. And let's make sure that this is correct, this interpretation is correct. Okay, so if we now look at the exponential form of the screw motion, okay, we have 0, 0, V0 times theta. So if we just write out the exponential, the series, okay, definition of this exponential, it's just I plus this. Oops. okay, plus 0v 0, 0 squared, theta squared over 2 factorial, plus so on. Okay. All right. So anybody want to try this real quick? This times itself. Can you do it in your head? What is it? 0. 0. So all these other terms, 0 goes away. Okay, so it's just this. So it's just orientation is I. Okay, this is v theta 0, 1. Okay, so that's why if you have a prismatic joint, okay, you want v to be the direction of translation. Okay. Okay, so there you go. All right, so once you understand how to write down a screw motion as an exponential and represent it as a formula, okay, there's no reason why anybody would want to use DH parameters. Okay, it's just so much easier, right? You don't have to worry about link frames. You don't have to worry about, right, choosing the frame in a correct way such that DH parameters exist. Okay, all right. So, so your mission, you know, when you're out of school and when you're out in the working world, is to educate the masses. Okay, tell them, look, this is the great right way to do force kinematics. Okay, throw out your DH stuff. Okay, this is what we want to do. I've been trying that for 20 years. Okay, progress is very slow. Okay. But hope springs eternal, as they say. Okay, so so I gave you your mission. Okay, go out, educate the world. Okay, tell them, you know, DH, you don't need it. Okay, this is better. Okay, but still, the fact remains: 90%, maybe more than 90% of the people out there use DH. Okay. So you have to be able to explain to them what's the connection between DH and this. Okay, so let's look at that now. Okay, so in the DH representation, we have rotation x alpha I minus 1, translation x ai minus 1 times translation z di and times rotation around the z-axis by theta I. Okay? Now, what I'm going to do is I'm going to say these three things, okay? This times this times this. I'm going to, okay, so it's a revolute joint. That's the joint variable if it's a revolute joint. These are constants, okay? Alpha, A, D will be given, so these will be constant. So let me just multiply these three things together, call it M sub I. Okay? This is a pure rotation around the z-axis. So I can write this as a matrix exponential. Okay? So it's going to be that times the matrix exponential representation of rotation, which we now know how to do. This is just e to the, let's call it s theta I. And what does s look like? Well, s in this case is a rotation, pure rotation around the z-axis. So s would just simply be 0 minus 1, 1, 0. Okay, and then we have Remember, this is a 4 by 4. Everywhere is zeros. Okay. So I can write it this way. Now, what if it's a prismatic joint? Okay. For prismatic joints, what do? What's the joint variable for a prismatic joint? We agreed that it was D. Okay? Okay, now, note that, okay, so here we translate in the z direction by D, and then we rotate around the z-axis by theta. Okay, so translate, rotate. What if we did rotate and translate? Rotate, translate versus translate, rotate. It's the same. It's the same. So we can switch the order. It's still the same. Okay, so translation in z di times rotation about z by theta I, okay, is the same as rotation followed by translation. Times translation z di. Okay, so if you have a prismatic joint, all we do is we just switch these two. Okay, we switch these two. And we can then still write, okay, still write in the same form, ti minus 1I in the same form, m sub I times e to the, okay, s theta I. But now what's s in this case? S is now, it's a prismatic joint, so it's translation in the z-axis, in the z direction. So this part's all 0. And we just have a 1 here, a lonely 1 right there. Okay, so that's what you do for a prismatic joint. Okay. All right, so that means based on the above, okay, we can write the for kinematics T0H can be written in the following form. It's m1 times e to the, say, s theta 1, m2 times e to the s theta 2. Okay, we need a little more room. Okay, dot, 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 e to the, oh, sorry, forgot an m here. M times e to the s theta n, okay? And then we might have a hand frame, T and H, okay? So that's from the transformation from link frame n to the hand frame, okay? All right, so we can write it this way. But this is not quite what we wrote. Okay, we have these m's stuck in the middle. Okay, so that's different from what we had in the product of exponentials formula we saw earlier. Okay, so we need to, it would be nice if we can move these m's away from the middle toward the back. Okay, so there's a way to do that. You know how to do it. Okay, so recall the following formula we used a lot. P times e to the a times p inverse. Okay, this formula is true for any square matrix A and P where P inverse exists, okay? For any matrices P and A and P inverse, always true. This is e to the a, or p times a times p inverse. Okay, always true. You know how to show this. Okay. Another way to write this. Move the p inverse over to the other side. Okay. Or another way to write this. E to the a times p is times p inverse is p inverse e to the pa p inverse. Okay, so just 3 versions of the same formula, essentially. Okay. All right, so I'm going to use this because this shows me a way where I can move the p in the front to the back. Okay, but the top changes here. Okay, so let's do that. Okay, so m1 e to the s theta 1 times m2 e to the s theta 2 dot dot dot. Okay, let's use that trick. This is equal to e to the s theta 1. Okay, oh, sorry, didn't even use the trick properly. This is m1 times s times m1 inverse. Okay, theta 1. Now m1 comes to the back. Okay, now we have the rest. m2 e to the s theta 2 dot dot dot. Okay, let's do it again. This time let's move m1, m2 to the back. Okay, so this is e to the m1 s m1 inverse theta 1 times e to the m1, m2 s m1, m2 inverse theta 2. And then we have m1, m2 over here times, right, m3 e to the s theta 3, so on. So you get the idea, right? Keep doing this. Keep doing this. Okay, and then eventually what you get is e to the s1 theta 1 e to the s2 theta 2 dot 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 e to the sn theta n times some m, okay, which is the form we want. Okay, and what is S1? Well, S1 is just M1 times S M1 inverse. Okay, S2 is M1 M2 times S times M1 M2 inverse. Okay, so on. Dot dot dot. And finally, this m, what is this m? Well, it's going to end up being m1 times m2 times up to m sub n times, I guess we have a t and h here. Okay? All right. So this is how you go from the dh formula to the product of exponentials formula that we learned. Okay, so you have a choice. Okay, you can use this formula. Okay, so somebody gives you a table with the dh parameters and a figure. Okay, so you can use this formula to convert the dh parameters to exponential form. Okay, or what I would do is I would just throw out the formula, rip it up, throw it away, start over, okay? Because it's so easy. So easy to find the S's. Okay, I can just look at it. I can look at the robot and just write down S1, S2, S3 just by inspection. Okay? Okay, but if you need formulas, if you want to write a computer program, for example, then this is what you would do. Okay? All right, I think now is a good place to stop. I didn't get quite as far as I wanted to, but we'll stop here and take the quiz.